Okay, I think we can get started here. Welcome back. So last time we were talking about 10.4 and we're going to move on to 10.5. So last time we left off with defining this scalar triple product and the physical relationship that it had depicting the volume of a parallelogram in R3. So let's kind of continue with that. And this kind of helps us with the idea of coplanar. We have to kind of define that. So if we have that A dotted with B cross C is equal to the scalar 0, in other words, the volume of the object that's created by these three vectors is equal to 0. The three vectors are coplanar. And this just simply means that they exist all on some shared plane. And that makes sense. If all three vectors are on the same plane, the volume that's created by that thing needs to be 0. It doesn't have any height, right? And that's kind of what we get from this, right? The volume is equal to 0 here. So if we have this relationship between our three vectors, any of our three, then like any combination of this, we have that our three vectors are coplanar. Okay, so let's do an example where we find the volume. So we're going to find the volume of the box generated from the vector A, which is I hat plus 2j hat minus k hat, the B vector, which is negative 2I hat plus 3k hat, and finally the vector C, which is 7j hat minus 4k hat. Okay, so the volume is equal to the absolute value of our scalar triple product between these. So we need to figure out this cross product beforehand. And in fact, we could do it the long way. We could do this cross product and then this dot product. But from last time, we wrote, so I guess let me reiterate here since that was from last time, that the scalar triple product could be calculated by the determinant where the rows were the elements of our vectors. So in this case, we're looking at the absolute value of the determinant of that's created by our scalar triple product here. So let's keep that in mind. We've got some absolute values to kind of work with here. And then we're looking at the determinant of 1, 2, negative 1, negative 2, 0, 3, that's not a 5. There we go. 3. And then 7, 0, negative 4. Remember, we're still taking the absolute value of this.
Isn't it 0, 7, negative 4?
Oh, yep, you are right. 0, 7. Let me erase this. There we go. Okay. So I have the absolute value, and then I have 1 times the determinant 0, 3, 7, negative 4, minus 2 times the determinant of negative 2, 3, 0, negative 4, plus our negative 1 here times the determinant of negative 2, 0, 0, 7. And we're still taking the absolute value of all of this. So this first term here gives us a negative 21. Then we have a minus 16. And then we have a plus 14, which gives us the absolute value of negative 23, or just 23. So simple enough. All we need to do is just the determinant of this 3 by 3. So not too bad. Okay. Leave a little bit of that up. And then we'll talk about the vector triple product. Okay, so the vector triple product is defined as A cross B cross C. So the output here is a vector, hence why the scalar triple product that resulted in the scalar is called the scalar triple product. And here we have the vector triple product. We're not going to work too much with the vector triple product, just so we're just kind of writing it down so that you've seen it. So if you kind of see it in any kind of literature, you know, hey, this is the, or just taking the curl, or sorry, not the curl, that's later. We're just looking at the cross product of these guys here. Okay, so let's finish up with the concept of torque. So we talked about work and how to write it in vector form. Let's also talk about torque. So imagine using a wrench to tighten some bolts. Okay, so let me try my best here and kind of drawing our little hex bolt, and then we're going to have a wrench here. Okay, so now if I have my hand on this wrench and I'm kind of trying to tighten it here, I have to consider two different things. I have to consider the radius from the center of where I'm applying this, force to where it's kind of being rotated around, the center of this bolt. And then I also have a vector that gives me the force that I'm applying to this wrench. And I might have to continue out this radius as well here. There we go. So we call this vector in here the r vector for the radius. And then here's our force vector that we'll call F. And then we'll have some angle between here that we'll call theta. Well, the torque is defined as, and this is a tau, as r cross F. So the torque vector is equal to r cross F. And we can also use the right-hand rule to kind of figure out where this torque is pointing. So remember the right-hand rule, we put our base of our palm against the plane that they share, and then we're going from A to B, right? So in this case, if I go from A, which is R, and I'm trying to go to F, and I need to make sure that the theta is in between 90 degrees, 0 and 90 degrees. So I have to use this one here. So I'm going from R to F. My thumb should be pointed into the screen, right? And notice that that means the direction of the force kind of implies that I'm tightening this wrench or this bolt here, right? Righty-tighty. So I'm kind of going clockwise. So I'm tightening this bolt, and the torque is going into the screen or into the material, right? That's why threads of bolts are threaded that way. So when you go righty-tighty, the torque is into the material. So another way that we can kind of characterize this torque is via its magnitude, right? So if I look at the magnitude of torque, it should just be the magnitude of R crossed with F. But last time, we saw what happens when we take the magnitude of this cross product. It's just the magnitude of R, the magnitude of F, multiplied by sine theta. And this might be where you've kind of seen torque defined before, right? It's this r, the radius, times the force, times the sine of the angle between them. But in vector form, we have to be a little bit more cautious than that, right? It actually has a direction that corresponds to it. And we write that as the cross product between the two. Okay, so that's pretty much it for 10.4. And then we can move on to 10.5. So let's start a new page. And we'll hop in to 10.5. So we're going to talk about the equations of lines and planes. Okay, so it's pretty easy to explain what a line is in R2, right? We've written relationships, right? Y is equal to X, right? Classic line in R2, right? But how do we write lines in R3? Now, Y is equal to X is not a line in R3. We looked at that the very first day, and that ended up being a plane because there was no Z restriction. So all Z values were allowed. So what's a good way of kind of characterizing this line in R3? So that's going to be our first goal here. You can imagine we've learned how to use vectors now. We're going to use vectors to kind of figure this out. So let's kind of start sketching what we might have going on here. So we have our z-axis, we have our y-axis, and we have our x-axis. And you can imagine that I've got some line that passes through in R3. So this is our y, this is our z, this is our x, and we have some line L. So L doesn't necessarily need to be a vector, it's just a line that just keeps going, right? It doesn't have a magnitude or, well, it has a direction, but it just goes on, right? So, but we're going to use vectors to kind of try to parameterize this line in order for us to kind of describe what's happening here. So I need a few things. I need the vector that points to any arbitrary point on the line. So we'll have here the point P. And P is anywhere on the line, but I'm considering it to be a specific point, right? L is the collection of all of the P points, but I want to kind of talk about how do I describe this one arbitrary point P. So to do that, I'm going to call this vector R. And I need a few things to kind of construct this R. I'm going to set a point on the line that will be my starting spot, and I'll call it P0. And I'll have some vector that points from the origin out to this point here, and I'll call this R0. So this is simply the vector that goes from the origin and points to the point P0. I also need some vector that is parallel with the line L. So I just need some arbitrary vector like this. And we'll call this vector V. So if I add V and R0, I'll start traveling along this line, right? And I can construct this R. How much of V I add to R0 will give us a different point, a different P. So if we scale V by either positive or negative amounts, we can travel along this line. So what we do is we say that R is our R0 plus T times our vector V, right? So at T equals 0, I just start at the point P0. And if I start to increment T, I start to travel along this line here. I'm traveling in the direction of V. Okay, so let's look at the components of these vectors, right? So we can rewrite this when we have that R0 is equal to X0, Y0, and Z0, some starting location. And we have our vector V is just some A, B, C. So that means that this R vector which is this we'll call X, Y, and Z, is equal to this R0 plus TV, which means that each component needs to line up. So we have 3 different equations. We have that X is equal to X0 plus AT. We have that Y is equal to Y0 plus BT. And then we have that Z is equal to Z0 plus CT. These are the parametric equations for our line, right? Each one of these depicts where the x, y, and z location is, depending on our parameter choice of t. So another little cool thing about this is we can solve for t in each one of these equations, right? T needs to be the same across the board, right? So if I look at my first expression, I have that t is equal to x minus x naught over a, but I also have that it's y minus y naught over b, and I also have that it's z minus z naught over c. And if I just look at these last three expressions here, I've kind of removed t from all of this, right? I don't have a parameter anymore. And this relationship between these three entities actually still constructs the line. It's all points that satisfy this relationship. And these are called the symmetric equations. So there's two different forms that we can kind of write this line. We could write it as a parametric equation with R naught plus TV, or we could write it using this relationship for the the symmetric equations, where we eliminate our parameter t here. Okay, so let's kind of figure out how we find this R naught and V so we can construct the vector R. Right? And let's do that kind of through an example here. So we're going to find the parametric equations for the line through the point -3 to -3, and we'll call this point P. And the other point that it passes through is 1, -4, -1, 4. And we'll call this Q. So this is all the information that we need to construct this idea of a line, right? It just passes through 2 points. Okay. We know that either of these points are on the line, right? So they're both perfectly fine candidates to make our R naught. Any vector that points to P or Q is perfectly fine to start with. I'm going to pick Q, I'm going to pick P, but you can pick Q and you'll get the same result at the end of the day. So we're going to set the vector R naught equal to -3, 2, and -3. So this is our starting location. The vector parallel with the line is the vector that goes from P to Q or vice versa. So I need the relationship from the vector between P and to Q. So I go 1 minus -3. I have -1 minus 2. And then 4 minus -3. So this is the vector 4, -3, and 7. So since it's pointing either to P or Q or vice versa, this vector is now parallel with the line. In other words, this is my V vector. Then we have that R is our R naught, which is -3, 2, -3, plus our V vector, 4, -3, 7, multiplied by our parameter T. So we can write out that X is equal to -3 plus 4t. We know that y is 2 minus 3t. And we know that z is -3 plus 7t. And this is a perfectly fine parametric relationship for the line that passes between P and Q. Like I said, you could have started with R naught being Q, and any direction for going from P to Q or Q to P will give you a relationship for some vector that is parallel with the line for the candidate for V. Okay. So let's talk about the distance from a point to a line. So imagine now that I've got some line down here, and I have some point P. Ooh, still a straight line. Some point P. The thing that I want to calculate is the distance from this point to this line, the shortest distance, right? So we're going to have a right angle right here. If I draw a line from the point P to our line. Let's go back and change color. If I know any point on the line, we'll call this point S, then what I could do is draw a vector from any arbitrary point S to the point P. This vector is S to P. I should be able to calculate the angle at which this vector takes, and I should be able to construct some vector that points parallel with the line. We'll call that vector V as well. We have a right angle here. So recall that the magnitude of our cross product is the magnitude of our vectors times sine of theta. Well, the thing that I want is this red line here. Well, this red line is the magnitude of S to P times sine of theta. And there it is on this right-hand side. We just have to divide over this magnitude of V. So in other words, the distance from the point to the line, which is S to P sine theta, is equal to the magnitude of S to P crossed with V over the magnitude of V. This way, I never have to calculate an angle, right? All I have to form is some arbitrary vector from S to P, and I need to find the vector that is parallel with the line. And this is the distance from P to that line, right? Never have to figure out what this angle is here. Right? And this works for any generic point S that's on the line. Okay, let's do an example for that. Let's find the distance from 1, 1, 5 to the line x is equal to 1 plus t, y is equal to 3 minus t, and z is equal to 2t. Okay, so first things first, let's look at the equations that we have for our line. This is r is 1, 3, 0 plus 1, negative 1, 2 times t. That's just me rewriting these parametric equations in terms of its vector form. So that way, I can kind of break this up. Here, I have r naught, some point that's on the line. And here, I have the vector v, a vector that is parallel with the line. And that's all I need to start talking about this distance here. So my S to P vector will be 1, 1, 5 minus our r naught, which will give us the vector 0, negative 2, and 5.
I have a quick question. How did you get V dash?
Excuse me?
How did you get V dash like 1 comma minus 1 comma?
You're kind of breaking up, but I think I got what your question is asking. How did I get this v vector? It's the coefficients out in front of t.
Okay, sorry. Oh yeah, okay, that's a 2. It looked like a Z, so I was confused. Okay, got it. Thanks.
Okay. So now that this is the vector that we're finding from S to P, we also need to find the cross product. So S to P crossed with V is our determinant here with I hat, J hat, and K hat. in the first row, and then 0, -2, and 5, and then 1, -1, and 2. So this is I hat with the determinant -2, 5, -1, 2, minus j hat with 0, 5, 1, and 2, and then plus k hat with 0, -2, 1, -1. We keep going, we take the determinant of this guy, we end up with 1, take the determinant of this guy here, we had to keep in mind that we've got that negative, so we get a 5, and then here we get a 2. Okay, so now we have everything that we kind of need here for this distance. So d, which is s, the magnitude of the cross product, divided by the magnitude of the vector v. So here we have 1 plus 25 plus 4 in a square root. And here we have the square root of 1 plus 1 plus 4. So we get the square root of 30 over the square root of 6, which just gives us the square root of 5. So a neat little way to kind of calculate the distance between this point and this line. I never had to find an angle, and it wasn't too bad. All I needed to calculate was I had to kind of look at my parametric equations here. I determined what my R naught and V are, and from there, all I need to do is construct this vector S to P, do the cross product, and do the magnitudes together. Should the 5 in the determinant be negative? This one here, yes, but there's a negative that's out in front of the j hat. Okay, so the recitation is going to take over in about 5 minutes. So I can answer some questions, but for everyone else that's content, you can take your 5-minute break, and then the TAs will be on in just a little bit. How did I get R is equal to 1, 1, 5 minus R? I don't know what you mean by R is equal to 1, 1, 5 minus R. This is the vector from S to P. So I know that this is some point on the line. And I also know that this is, this is some point that I'm trying to find the distance to from the line. And this is some point that's already on the line. So to find the vector that points to S to P, this is the vector P minus the one S. Let's see, both Heather and Teddy are on. Hello, Heather and Teddy, if you can hear me.
Hello.
Howdy.
So I guess I just sent them off for their 5-minute break, so you can start up in about 5 minutes or so, probably exactly at like 1:30. It looks like I have another question here. How did you get the determinant? The determinant of the 3x3 or the 2x2s? the 2x2s. The 2x2s are the on diagonal here. So for instance, for this first one here, we've got -2 times 2 minus -1 times 5. So in this one here, I get a -4. And then here I subtract a -5. So I end up with just 1. This one here, I've got 0 times 2 minus 1 times 5. So that's a -5, but I have this minus sign out in front. So I get a +5. And then here I get 0 times -1 minus 1 times -2, which results in just having this 2 here.